This presentation covers the JMP interface to MATLAB. My name is Daniel Valenti. I'm one of the product managers at JMP, Statistical Discovery from SAS. JMP scripting language, or JSL routines in JMP, allow you to initialize a MATLAB connection, send data to MATLAB, submit MATLAB code, and bring data and output back to JMP for further analysis or data visualization. The basic execution model is to first initialize the MATLAB connection, perform the required MATLAB operations, and then terminate the MATLAB connection. It's similar to our R interface in that it's a behind-the-scenes connection. And in general, we say that it's intended for finished MATLAB algorithms. MATLAB itself is a better IDE for developing MATLAB programs. So if I open up this script, this will generate a small interface which will allow me to connect to MATLAB. There are two buttons here: initialize or initiate MATLAB connection, a status text, and then a button to terminate the MATLAB connection. So when I click this button, it will run script, JSL script in the background, which will initialize the connection, set a control variable to 1, and then submit some MATLAB code to clear all, close all, and give my status to green. When you're first beginning to use the JMP interface to MATLAB, there are a couple setup items that you must take care of before using the interface. MATLAB must be installed on the same computer as JMP. The bitness of MATLAB and JMP must match. So if you're using 64-bit JMP, you need to be using 64-bit MATLAB. And because MATLAB, there's so many different versions of it and the install is pretty open, you have to set through the platform preferences in JMP the path to MATLAB root. So you do this by initializing a platform preference script and setting the path variable to the location of the MATLAB install. So you can see this is where my 32 and 64-bit installs are. And because this is a 64-bit version of JMP, it's going to be accessing this R2012B version of MATLAB that is installed in my program files in the MATLAB folder. You only need to run this once, and then JMP will store this platform preferences so that every time you use the interface again, it knows where to initialize that MATLAB connection. All of the available functions are available in the scripting index. You'll find the scripting index in our help scripting index. This is a very good utility in general for learning about different functions available in JSL, but you'll notice one of the categories is MATLAB. And in the MATLAB selection, you can see that there's a number of functions available to use JMP with MATLAB. So clicking on any one of those functions, such as the MATLAB send function, will give you the syntax, a description, and then an example that you can run. Now that we've configured the preferences, we're ready to get into a simple example. So for this, we're going to run the required MATLAB commands and then return results from MATLAB to JMP. As an example, we're going to be using the MATLAB magic square function, which is part of the built-in tools in MATLAB, with the syntax m equals magic of n, and this is going to return an n by n matrix constructed from integers 1 through n squared with equal row and column sums. And we want to turn those into a JMP data table. So here's the syntax required to do that. We can execute MATLAB code by using the MATLAB submit command, and then anything wrapped into the quotations here is MATLAB code. So in this case, we're going to submit m equals magic of 3, and this will return the results to this M matrix in MATLAB. Now, in order to bring the results from the MATLAB variable space to the jump variable space, we're going to use the get command. So we can MATLAB get that matrix M, then we can show this in the log, and then by using the asTable command, we're going to turn that matrix into a data table with the columns name 1, 2, and 3. I can run this script. You can see in the log we've returned the values in our matrix and also the values in our jump array. And then this has created a data table called Untitled 8 with the columns 1, 2, and 3 in the results. So even though this is a simple example, you can start to see the power here. We've taken the results from a MATLAB function and turned them easily into a jump data table. And now from here, I'm ready to use any of the built-in functionality in jump, like the distribution platform. And now I can, through JMP's interactive linking, start exploring the data, the output of my MATLAB functions. I can look at summary statistics, and I can look at graphing these data in any of the platforms available in JMP. This is a very simple example, but again, it shows the power and how easy it is to get from a MATLAB output to a JMP data table. What if you want to use pre-existing MATLAB code, though? You may have a whole library of pre-existing MATLAB code that requires the use of multiple functions and different files within a folder. It's important, and you need to tell MATLAB where these files are so that the instantiation in JMP can access those custom functions. And the easiest way to do this is through a MATLAB submit statement. And you can submit the file path that you're interested in pursuing. So again, here's a script here. We'll just submit a close all, clear all, and CLC. And then with a submit statement, I'm going to cd into the directory where this demo is. So if I run this and then bring up my MATLAB command window, I can see the list of all of the functions available, and several of these functions are .m files. And now I'm able to, through the interface, access all of my pre-existing MATLAB functions. So let's see how this works in another simple example. So I have a function that simulates an approximation to Brownian motion. It's a random walk with normally distributed jumps. This is in a MATLAB function called Brownian. So in order to take advantage of this function and to get the data into JMP, I'm going to again clear everything and then submit where this function lives. Then I'll submit the Brownian function with an input argument of 1000, so I want to generate 1000 data points and store this into a variable sample. Then I can grab this sample using the MATLAB get function and bring it into the JMP variable space, and then using the asTable command again, create a sample with a column names Brownian. So let's see how this works. So here are results from our simulation with data back in a JMP table. Now if I want to see what these data look like in graphical form, I can use the graph builder. And if I drag and drop, I can get the data there, but because this is really a time series, I'm interested in seeing how these data change over time. Now my function did not include a sample. I don't have a sample number here, but that's easy enough to do with the transform columns. So if I right click on here, I can go into the row function, and now this will create a temporary column for me called row, which I can rename to sample. Now if I drag this in, I get what's really the output of the data, which is how my function is changing over time. if I want to go ahead and store this to the data table, I can right click and now this virtual column becomes a data table column. So in a few clicks I was able to generate a graph, create a transform columns that represents the sample number, and then store that back into my JMP data table. This does not require me to go back to MATLAB and change my function based on my exploration. Similarly, I can use the distribution platform to get a sense of the distribution of my data. Summary statistics such as mean and standard deviation, which I can customize easily. I can add or subtract summary statistics. And quickly explore the data and the output from my simulation that I can use to continue to build up and refine my simulation as I'm in the design stage. Another area where MATLAB has rich functionality is in its solvers. So in this example, we're going to solve an initial value problem using the ODE 45 solver, which solves non-stiff differential equations. This problem comes from the book Numerical Computing with MATLAB. It looks at a paratrooper falling of a given mass. The paratrooper is accelerated by gravity, but decelerated by drag on the parachute. What we want to do is look at velocity versus time of 3 different mass paratroopers in JMP. Here's the governing equation where m is the paratrooper's mass, g is the acceleration of gravity, v is the trooper's velocity, and the initial velocity is assumed to be 0. So here's the JSL script that allows us to execute that MATLAB function. Again, I'm going to cd into the directory where this demo lives. In JMP, I've stored 10 to a variable here which represents the end of my simulation. I'm going to send that to MATLAB using the MATLAB send command, and then I'm going to execute the simulation for 3 different weight paratroopers. I'll return the values from MATLAB to JMP in each case, and then I'll build a table of all of these different simulations. So here are results where we have the time and velocity of all 3 simulations. Now, since the time of the simulation is constant in all cases, we can go ahead and delete these columns for time and rename this time because they're the same for all cases. And now we have the velocity for each of our 3 paratroopers. So again, we'll go to the graph builder to build our visualization. Now you can see that 10 seconds may have not been a long enough time for all 3 of our paratroopers to reach terminal velocity. Looks like this green paratrooper is still accelerating at the end of the simulation, which we've found out easily through our data visualization here. So now we can go back to our code and let's change the simulation from 10 seconds to 30 seconds and run the simulation for a longer time. And go back to the graph builder. And now in all 3 cases, we've reached terminal velocity. This first case looks at an application in signal processing. And it shows an example where you can extend the capabilities in JMP to process data using a previously written MATLAB function that you've developed. And the idea here is that you want to take data that you already have in JMP, send it to MATLAB, process it with some function. In this case, we're going to be doing a frequency transform. So we're going to use an FFT function in MATLAB to convert frequency data from the frequency domain to the time domain, and then bring the data back into JMP. And we're going to deploy this out into an application that looks very similar to many of the analysis capabilities in JMP. So in MATLAB, the FFT of x function is the discrete Fourier transform of vector x. And in MATLAB, you can send an arbitrary number of samples, and it's a very fast algorithm. And what we want to do is build an application to perform this conversion. So this data set in JMP represents data that was measured using an impulse response measurement technique. And we have sample from 1 to 25,000 and then amplitude. So these are data that are in the time domain. We can visualize this using the graph builder. We can see that these data represent an impulse response. So the technique is to send out a test signal into a room that we're trying to characterize. This is a logarithmic sine sweep from 20 Hertz to 20 kilohertz. And then we record it with a microphone and then deconvolve it and basically take the known test signal and what we measure, subtract the two, and what we're left with is how sound decays in the room. So we have the direct sound and then all of the reflections as sound decays over time. While these data are informative in the time domain, it's often interesting to look at how the frequency response of the room is. And for that, we're going to need a Fourier transform. So this program that's written in JSL basically will build me a launcher that will let me transform data from the time domain to the frequency domain. And what's nice is if you have users that are JMP users that you want to empower by giving them access to your MATLAB code without having them need to use MATLAB in the background, you can simply wrap up any of your algorithms into an application like this. And then all the user needs to do is put the required columns into the response role here, click OK, and now their data is processed and returned to them using your functions. They don't have to ever touch the MATLAB code that's going on behind the scenes. So very similar to what we've done in the past, we're submitting where this code is. We're going to send the vector, which is what the user has selected in the launcher. And then we're going to submit our MATLAB function, which in this case is calcFFT, with the vector, sampling rate, and because we're going to do all the plotting in JMP, we have our plot switches off, which was part of this original function. Then we're going to get the FFT signal, get the frequency array, and then build a new table. And now we have our transformed columns, our frequency array and the FFT signal. If we want to visualize this frequency response, we can drag these two things here, and then frequency is often displayed on a logarithmic scale. So I don't have to go back and think about plotting these data on a semi-log or log-log scale. I can just double-click the axis specifications and change this from linear to log. Look at frequencies from 20 Hertz to 20 kilohertz. And now my data is on a log axis. And turn this smoother off. And because everything is linked in JMP, you can select areas that are interesting, like this peak here. Back in the data table, you can see that all of the rows that I've selected are also selected here. If I right-click and want to color these red, I can click that red, and now they're colored red on my graph here. I also may be interested in seeing information about the nature of the FFT signal. So here's a distribution of the response. Here are all the points in the noise floor. If I want to, stack this here so I get a better sense of the distribution. I can add a continuous fit, such as a normal curve or a normal mixture. And I get all of my statistical output here for the location and dispersion probability. I can adjust the histogram. I can change the color here, add a shadowgram. Change my confidence interval. Look at a cumulative density plot, and have lots of built-in functionality to explore these data without having to write any additional code. If I use the fit y by x platform with frequency array as my x and FFT signal as my y, I can use the power of a nonparametric density to look at where all the weight in the signal is. So I have clusters here. If I turn off the points, I can see where all of the densities are in a nonparametric way. In this case, we're going to use the custom design functionality in JMP to set up an optimal design of experiments to optimize a computer simulation that's written in MATLAB. The custom designer in JMP is an easy way to set up an experimental design to fit the specific problem you are facing. We can use JMP to set up the experimental conditions, perform simulation runs in MATLAB, and then analyze the data that's returned or explore a model's opportunity space interactively with the profiler. So this is the case where you often have pre-built simulation models in MATLAB that need tuning of multiple variables. And if you have a lot of different variables and you're trying to optimize the output, if you're sweeping through individual variables, you can easily get into a situation where you're running thousands or hundreds of thousands of runs to cover the space. The other situation where you may want to take advantage of these capabilities if you have real data and simulation data, and you're trying to match the simulation data to the real or behavioral data. We're going to use JMP for the automated generation of conditions, running the model, and then storing the data in JMP data tables. So this is a JMP table with the factors that we're going to be exploring in our model. Our MATLAB model has 5 input variables, x1 through x5. And these are the ranges that we're exploring: x1 from 0.7 to 1.7, x2 from 1.8 to 2.3, x3 from 40 to 60, and then x4 and x5 from -10 to 10. So if we were to sweep these x1 and x2 at a 0.1 step, x3 at a 5 step, and then x4 and x5 at a step size of 1, we'd have 132,000 different conditions we'd need to run to see how those factors affect the output. So by using the custom designer in JMP, we're going to cut down on those simulation runs drastically. So the custom designer is in the DOE menu under custom design. And our goal here is to maximize a single output y. Because I have these factors in a JMP table, I can go into the red triangle and click Load Factors. And these automatically are in the factor section of the DOE platform. I'm interested in main effects, factor interactions, and then also looking at curvature, possibly in our model. So by clicking the RSM button, this is a script that will generate all of the main effects, the power terms, and then also all of the second order interactions. You can see from those selections, I have a default design of 27 data points. I can also, if I want to add more runs to this, I can go into the user specified. So if I want to run 32 runs, I can do that. I can click Make Design, and then this will generate all of the different runs and the factor settings which we're going to use as inputs to our model. If I click Make Table, I now have the data table of all of the different runs and my Y. Also in the Custom Designer, under the red triangle, you can see there's an option for Save Script to Script window. And what this will do is it will generate automatically the JSL required to generate this design. And this becomes very important when we're trying to build a script that will automatically run the MATLAB simulation model. So if I open up this script, you can see I've already copied the DOE script that we had here into our function. From here, I will make the table called design. I'm going to again use a MATLAB submit function to tell JMP where the location of my simulation model is. And then I'm going to use the for each row command and then grab the levels of each of my columns for variables x1 through x5, send those 5 to MATLAB, and then submit my simulation model with the values for each of my 5 input factors. Then I'm going to return that to a variable called yield, get the yield, and then place that in the response column for each of the rows. I've repositioned my window so we can see the output of each of the runs being written to the log. So when I press run, JMP will create the design, and then in the log you'll see the results for each of the runs and the factor settings for each of those trials. When all 32 runs are done, the results will be written into my data table into the Y column. And you can see the potential time savings by adopting a design of experiments method into your simulation models. Even at 1 second per run, by reducing the trials to 32, will give me quite a bit of time savings over trying to sweep through the ranges in my simulation model. To analyze this model, I can go into Analyze Fit Model. And JMP knows the model that I specified in the design. So the model effects include the main effects, the polynomial terms, and then all the two-way interactions. This is the output, which shows the actual by predicted plot, an R-square value. In this case, we have an R-square of 0.97 and R-square adjusted of 0.92, so we're getting a pretty good fit to our data. The analysis of variance, parameter estimates, and then what we're really interested in is this prediction profiler, which shows us the opportunity space of the model. So as I click and drag any one of these bars, you can see the value of my yield based on where my factor settings are. And I can also see the impact that one factor has on the slopes of the other factors. So any interactions that are present, I can see these easily by clicking and dragging these bars. I can use another tool called the variable importance, which is in the red triangle for the prediction profiler. And this will allow me to get a sense of how important each factor is in my response. So when I click on those Assess Variable Importance options, I get an ordered list of my effects. So I can see X3 in this case has the greatest effect on my response, and my profiler has automatically been reordered with my dominant effects on top, so X3, X1, and X5, followed by X2 and X4. So this becomes a powerful tool if you are iteratively improving and adapting your model based on your runs. So I can right-click on this report, click Make into Data Table, and now I have the main effect and total effect of each of my factors. If I give this an iteration number and then improve my model, I can track how these different factors affect the response over my different iterations. So it's very easy to take any of those charts here and start to store this into a summary data table. This prediction profiler can be saved as a .swf file. All you have to do is go into the red triangle. You can save this formula and then go into Graph, Profiler, and then click Save as Adobe Flash Platform. And now this Flash platform can be embedded in a PowerPoint presentation, or in this case, embedded in a web page. And it preserves that functionality, which makes communicating the impact of factors on a response in your different models very easy and graphical. Today we presented the JMP interface to MATLAB. We showed the basic execution model with several examples. We also showed two cases. The first case was an application for signal processing, using the FFT function in MATLAB to convert data in the time domain to frequency domain and return results to JMP for data visualization and further analysis. Then we used JMP to design an optimal experiment and run conditions of a simulation model. We returned results to JMP for analysis and interactive profiling, and also assessed variable importance. And in both cases, we're using JMP as an analytic hub to reach out to pre-existing or new MATLAB functions. Then we can return data to JMP for analysis, visualization, and further exploration.